Alright, hopefully a short video because it's a Friday afternoon and I'm tired. Just kidding. Yeah, I only have two examples here, but that of this topic it should be enough, I think. Free energy, as we've been talking about it, and entropy and enthalpy, but the free energy is actually dependent on pressure and temperature, I suppose you can say, and some other factors too. Everything that delta H and delta S depend upon, of course, affect the delta G. But thinking back to entropy and the degree of messiness of the system, should we say? We could say that, larger volumes of gas, in particular, or just larger volumes of whatever, could be solids and liquids, I suppose. Easier to think about and tabulate gases. Larger volumes of gas have more entropy than smaller volumes. But then we think back to Gen Chem 1 and about how pressure varies as the reciprocal of the volume. That would mean, I suppose, that low pressures and large volumes have more entropy, less entropy, more entropy than smaller volumes and higher pressures. Well, if you carry that logic out and do some calculations, it's not hard to show that the free energy change during a reaction is equal to the free energy change under standard conditions. And plus or minus a little factor here depends on Q, and Q, think back to equilibrium, is our reaction quotient. Especially for gases is this important because gases can vary in pressure quite a bit, So for example, if I had, can I get this right on there? Excuse me. Right there. Cool. So if I had 1 atmosphere pressure of this gas and 1 atmosphere pressure of this gas and 1 atmosphere pressure of this gas, do you remember how to write Q? It's like this in the numerator squared and this in the denominator and this in the denominator squared. But if that's 1 and that's 1 and that's 1, it's all 1 over 1, and it's 1 over 1 is 1, and the natural log of 1 is 0, and RT times 0 is 0, and the free energy change is equal to the standard free energy change. Whoa. But you know what? They aren't 1. So Le Chatelier would say, what if I had a whole bunch of this and only a little bit of this? Carried it even to a larger extreme. What if I had 200 or 2,000 atmospheres of NO2, but only 1 atmosphere or 0.1 atmospheres of these two? Le Chatelier would say too much of this would lead to the reverse reaction, the holding back. The standard free energy change for this is negative 71 kilojoules. So that kind of means it tends to go in the forward direction. But this little circle up here means standard conditions, which includes 1 atmosphere pressure of gases. So since I'm not at 1 atmosphere, I'm going to predict this is going to rather want to go backwards or hold backwards or not be as spontaneous in the forward direction. So I'm going to predict that negative 71 becomes not quite so large in the negative direction, and therefore, there it is. There's the answer. So what do we have? So here's my standard free energy for that reaction as given to me. The gas constant in energy units of joules or kilojoules. Since this was in kilojoules, I changed this to kilojoules. My Kelvin temperature. Think back to on equilibrium to remember how to write this. It's the products over reactants. It's the NO2 on the right hand side is a product square. There's a 2 in front. And this is how we wrote our equilibrium constant expression, but it's also how I write our reaction quotient, saying I'm not quite at equilibrium. Again, if this is 1 and this is 1 and this is 1, it would be 1 over 1. The natural log of 1 is 0, and this times 0 would not be any term at all. So this 20.5 wouldn't be there if this was 1. But since we're not at 1 atmosphere standard conditions, this negative 71, gets less negative and less spontaneous in the forward direction. But I suppose it's still negative 50, so at least to some degree it still wants to go forward, even though I have a whole bunch more in terms of pressure of the NO2 than the NO and the O2, because that is such a large negative free energy change, standard free energy change. free energy change during a reaction depends on the standard free energy change, and also something about the pressures, if the pressures of gases are not 1 atmosphere. Alright, time for the Jeopardy music. If you're a motivated student, you might pause it and try this question. Wait time? That's enough. Here's my reasoning. Here's what I'm thinking. Is this reaction spontaneous in the forward direction as written? It says under 700 Kelvin. Man, that's pretty warm, but even though this is referenced probably at room temperature, it probably doesn't change too much at warmer temperatures, but it could. But let's just assume it doesn't change too much. Is it spontaneous? Positive 46? No. Doesn't want to go forward. But if I make this into, and that's reflective of 1 atmosphere and 1 atmosphere and 1 atmosphere pressure of each of these gases. But what if I made this 33 atmospheres, this 99 atmospheres, and this 2 atmospheres? What would Le Chatelet say about that if he was still alive? He'd probably say, wow, that's a lot of gas over here and very little relative over here. So 33 and 99 of these to the cubed power, goodness gracious, isn't that going to want to make it go forward because there's only 2 atmospheres, relatively little of gas pressure over here? And yeah, so what's the take-home prediction? I would say since it wants to go forward, this positive is going to become less greatly positive, perhaps even down to 0 or even negative. Let's try it. How do I write Q for this expression? Oh yeah, wouldn't it be the 2 in the numerator squared and the 99 in the denominator cubed and the 33 in the denominator of that quotient? And indeed, the natural log of that ratio came out to be negative almost 16 times 5.8. Whoa, it was 46.4, and coincidentally this term is almost twice as large, negative. So now the spontaneity quote turns around, and it went from being not spontaneous under standard conditions to these large pressures of N2 and H2. And indeed, as I understand it, that is one of the ideas in making ammonia gas, to make this very negative and more likely in the forward direction. Why don't I take a whole bunch of this and a whole bunch of this and a little bit of this, and as a matter of fact, as the reaction starts to make this, find a way to remove it from the vessel. So the reactants think we trick them into saying, wow, I'm not making very much NH3, I better keep on going. And so if I had 33 atmospheres and 99 atmospheres, it really wants to make this, that positive free energy becomes very negative. Whew, does that make any sense? That's very logical. I hope you had a cup of coffee or maybe a soda before that. Or maybe go have one and go rewatch the video, take some notes, ask me a question, ask your TA a question. Thanks for watching, guys. See you in class.